Well, thank you for braving the winter blizzard. I see that there are a lot that did not brave the winter blizzard. It's supposed to get warmer. Anyway, we've got a hot lecture today, and that is a lecture which connects a quantum mechanical equation, it's called Schrodinger's, to the coupled oscillator equations we talked about in the last couple of lectures. So what I would like to do is first of all point out at the very bottom of the screen and your things that you'll get online a link to a lecture on how you handle repeated eigenvalues and what sort of pathologies come up when you have matrices that give a degenerate set of eigenvalues, that some two eigenvalues that are equal. That's degenerate already, but you're talking about systems with high symmetry, degeneracy can be very large. And that makes it a very interesting problem, because as soon as you have energy levels that are the same, all of the states that are associated with those can talk to each other through resonance, perfect resonance. So that's why group theory becomes very important for systems that have extreme amounts of symmetry and the resulting resonance. And we're hoping we'll have a course on that coming up in the spring. So if you're interested in learning about that stuff, that's my advertisement for the day. In any case, what we'd like to do today is take this stuff that we talked about in the last lecture, in particular a matrix operator equation. The simplest form with a mass matrix is this, but we made that into a unit matrix and subsummed the mass into the spring constants for the benefit of simplicity. And we're looking for the thing that we looked for and talked about in the last lecture were those very special directions where the k times x is in the same direction as x in whatever space you're dealing with. In other words, the eigenvectors. But today I would like to just concentrate on the connection between a very classical problem that we were talking about, which is a second order, a differential equation, and the very famous Schrodinger equation, which is a first order in time differential equation with a little I and a scale factor in front of the time derivative. So what I'd like to do right here, and I'll do it on both screens here, and we'll keep some of this stuff when we get results available on that screen over there. But the basic idea that I want to get across is that this is a chance to learn also about the generalization of complex numbers to spinor operators. And those are the 2x2 matrices that define all of the algebra that you need to do for any two-level system, whether the levels are degenerate, in which case not much happens, or when they're not, and that's when the activity that you're interested in occurs. In any case, what I want to do is first of all take the Schrodinger equation completely apart into real and imaginary pieces. And it's a shame that I've seen no quantum textbook that does this. They just work out the Schrodinger equation and then never take it apart. But when you take it apart, you get to see the relationship between what you're doing in quantum mechanics, which are resonant modes, and classical resonance modes. And that makes it, you can learn a lot just by doing that. So in any case, what I want to point out here is that this H matrix, having to be Hermitian, that means self-conjugate. That means if you do a transpose of this matrix and conjugate it, you get the same matrix. So that means that this off-diagonal component here of a 2x2 Hamiltonian, quantum Hamiltonian, has to be equal to the conjugate, complex conjugate of the other side. And the diagonal elements have to be real. So that cuts you down to having exactly 4 parameters in a quantum mechanical 2x2 system. There are no more parameters than that. It's not complex numbers everywhere. That would be a lot more. Instead, there's only 4. And then the states that you deal with in quantum mechanics, they also involve 4 parameters, the real and imaginary parts of both components. And we're going to make the connection by saying that the real part is a x value of a phasor, and the imaginary part is the momentum scaled appropriately part of. That's just the first base state. The second base state is the same thing with a number 2 on it. So the idea that both the Hamiltonian that drives this state and the state itself have exactly the same number of parameters, and that's an arithmetic truth, that 2 plus 2, 2 times 2, and 2 to the 2 power, they're all 4. Okay, so with 2 dimensions we've got some interesting symmetries and connections that we can build later for bigger matrices, but let's just get this one done first. So what I'm going to do here is take the Schrodinger equation apart. That is, I'm going to separate these real and imaginary parts and see what real first-order differential equations you get when you do that. And of course, if you're going to program a 2-level system, that'd be a good start right there. And then over on this side of the board, we're going to talk about that guy that we talked about in the last few lectures. So basically what the setup here is that we're talking about a partial derivative with respect to times I, and then we've got 2 complex numbers here. And then we have a matrix here that's complex, but it's Hermitian. That makes it a little simpler, and there's the same state again. Okay, so what I do then is I simply write out, I pull out the imaginary part, that's the red line here, and set that equal to x dot 1. And then I pull out the real part, it's now a real part because I took an I here and multiplied by that I, that makes a minus sign right there. I take out that real equation and set it equal to all the real parts that this matrix has given me when it multiplied the state. And then go ahead and line these things up now. This is the first real equation, x1 dot is equal to a, b, and c with various momentum position. And then p1 dot is the same idea. It's got some minus signs here, and it's a, b, and c, just like this one. But then the second component has b, d, and c in both of these spots. So there are the ordinary differential equations that quantum mechanics, 2 states, is going to have. Okay, so far so good. But now what I'd like to do is, and this is a big jump right here, is I would like to start with a classical Hamiltonian designed to give this result. So here is a classical Hamiltonian H sub c, okay, C for classical here, with the parameter A sitting in front of P1 plus X1 both squared. And then a coupling coefficient, it's kind of a spring thing, but we'll talk about what that really is, times the product of X1 and X2 plus P1 and P2. And then this one, X1 P2 minus X2 P1, that's sort of an angular momentum in 1-2 space. And so the C goes there. We'll talk about that C. And then the D goes for the second component, sum of P and X, both squared. Okay, so we simply apply Hamilton's equations to this Hamiltonian. And now this is only true here for constant A, B, C, and D. So you got to keep those guys constant, or there'll be other terms corresponding to derivatives of whatever the A's, B's, and C's were doing. This is somebody working from the outside on the motion. So here are the differential equations that come from this thing. And the idea is this thing is, let's be honest, designed to give the same result. That is, these set of equations are identical. Okay? All right, so far so good. Quantum versus classical. Equations are identical. If you make this guy. Okay, and that's kind of a weird Hamiltonian. Okay, we'll see how weird in a minute. All right? But this is a very, very solid link between what happens in classical mechanics and what happens in quantum mechanics. And you use the two against each other. Most of the time, things over here are pretty easy to understand. Things over here may be less so. Well, you take those guys over here and figure out what's going on over here. Okay, now what we're used to, of course, in the classical world is having second-order differential equations. We're talking about F equal ma, right? The a is a double derivative, so you've got to live with that. But let's find out how you could do it some other way. How could we handle such an equation in another way? And so what I'm doing here is I'm just going through here and taking a second derivative of this thing so that I can write this P1 dot here as a double P dot, P2 dots, okay? And so I stick that thing in there and put the minus sign on the outside and so forth. And I do the same thing on down the line here. So I get x1 double dot and I get x2 double dot, and they're made of combinations of, obviously, quadratic in those constants a, b, c, and d. So here is what the equation that you would probably be more used to is a second order classical Newton-Hooke-like equation. Okay, Hooke law being applied to the springs. But we got some more stuff here than just that. If I set this parameter c equal to 0, I immediately get something that looks exactly like the coupled oscillator with spring constants and a mass of 1. If I have an x and a y coordinate, x1 and x2, and this is the acceleration of that coordinate, double dots, this is minus a k matrix times position. So we've seen this before. But the idea is the quantum mechanics has a little bit more to offer. It has that c to offer. And here we've set it equal to 0, and we only have a, b, and d left in classical physics. So at this point you say, okay, I have an operator view of a connection between the Schrodinger quantum equation and a very special classical oscillator equation. It's also something that's been taken out of that quantum mechanical system that had 4 parameters. We're down to 3. Okay, but what's interesting about this is that I can see this one at least as the square root of the Newton-Hooke equation. That is, I just literally take the whole square root of x dot dot minus kx. Now, what's going on there? Well, better way to do it is to probably go the reverse and say, what happens if I square this equation right here? I square that operator and I square the h. Okay? Well, yeah, that's what we did. That's what turned up here. This thing squared is exactly what we need to make an equation that is both classical and quantum. But the c is missing. Well, it turns out we didn't really have to do that. I just go here and I transform the Schrodinger equation, Schrodinger operator, directly to the square of that, and the I squared gives you a minus sign, okay? And of course the square of the differential operator gives me a second order acceleration, and then this thing squared gives me this, which is a little bit more complicated than what we were getting up here, but the c is now included. Okay, so this is a very direct way. I could have skipped all of this stuff and just done this, right? That's your connection right there. The stuff that you do in quantum mechanics with 2 levels, squared is immediately a classical coupled oscillator with an extra thing c. Well, let's see what c does. but without it, it's what we were talking about in the last lecture on Wednesday a week ago. Okay, so that's what we have here. Now, the solution to these, a solution to a first order differential equations with a constant operator is just the exponential of that constant operator. Well, at this point I could say, well, we could go back and use our projection operator stuff, right? And take any function of the Hamiltonian we want, including exponential. We took the square root, and we took the 50th power, just as an example. You can also take an exponent. But what we're going to show today is a cool way, which Pauli, Hamilton discovered for doing this, for visualizing what this operator does. Not only what its numerical value is, but what it does, how it works, what it is like. And then to do that, we're going to be generalizing complex arithmetic to what I call spinor arithmetic, to complex vector algebra. Remember how we show the cross product and the dot product? Spinor vector algebra is very much like that. And then finally the exponential, the thing we really need here, which I call the crazy thing theorem, spinor exponentials. That's what we actually need here. We need e to the minus h, and h is going to be a combination of these spinor operators that Pauli claims he discovered, but he didn't. It's Hamilton that discovered that algebra. It's called quaternions. Okay, so that's what we're headed to here. And now I'm going to actually give some mnemonic names for the parameters A, B, C, and D. The A corresponds to what you get if you take this matrix apart into a unit operator, which has A plus D over 2, and then A minus D over 2 times this thing. That takes care of the matrix if there weren't any B and C off diagonal. All that does is set you up with an A and a D. Okay, but if I turn on the B, that's kind of like the coupling that made us go from having our ellipses all lined up with the x and the y axis and tip it a little bit. Okay, if you tip it a little bit, or 45 degrees is actually what we tipped it to, so that we had a matrix that looked like this. The coefficients on the diagonal were the same, and so were the counter diagonal. So that I call B for bilaterally or balanced. And then the C operator, that's the weirdie. Okay, that's the one that makes things go. That's the one that makes currents happen. Things start rotating when you turn this guy on. Okay, so C, current carrier. It's also the things that gives the thing chiral, left and right handedness. It gives you circular polarization. It gives you complex eigenvectors. It is the effect of Coriolis and cyclotron effects. It has curl. So a whole bunch of things that start with C are hiding behind that parameter. Okay? Nice mnemonics, right? It always helps to have that. Now, Pauli's names are very different from this. And so are really quite Hamilton's. But we go to 1927 when these were first published by Wolfgang Pauli. And they were known as the Pauli spin operators. Sigma 1 was just a unit matrix, but then the other three are what we're really interested in here. The unit matrix is sitting right here, but these are the things that make things happen. And the thing that we call bilaterally balanced is a Pauli X. What we call curly, chiral, Coriolis, cyclotron, whole bunch of names. That's the Y of Pauli. And then Pauli Z, that's our good old diagonal, asymmetric diagonal A matrix. Okay, so this is just a little bit of switcheroo that you're going to have to get used to, but I made the mnemonics a heck of a lot better than Pauli's. X, Y, Z, what's that mean? Okay, but A, B, C, and D, they do mean something. Okay, now, Hamilton's quaternions. This comes in 1843. That's a heck of a long time between his discovery and Pauli's. And it's kind of amusing that he doesn't give much credit to Elliot. But these things are simply, what he calls them I, J, and K. And they later were picked up by the American physicist Willard Gibbs, who used them as the unit vectors of x, y, and z. Okay? And the unit operator is just an afterthought. So after you put a complex number I on each of the Pauli operators, or our little a, b's, and c's here, you immediately get, in this case, the x is the I, j, and k respectively for the y and z. All right? So that's kind of the history, a little bit of a nutshell history for these. And Hamilton's quaternions square to -1. Whereas the Pauli operators very conveniently square to +1. So putting that I on makes those three, these three right here, square up to -1 rather, -1 unit matrix, and the others make up what's called the quaternion group. That's a little bit of group theory that we don't need to talk about right now. Okay, so that is the comparison right here as far as being squares. Each of these operators makes what's called a cyclic group. It's just a group of a unit operator and that operator, which when squared gives that back again. We'll be using that group sooner or later, mostly later. Okay, so here's the deal. Here's what we need to have. We need a way to convert this exponential of a Hamiltonian times time with a -I to a matrix that we can just read off. We want to get this thing understood. And it's a generalization of this, the Euler formula, okay, that we're going to be getting. It's a generalization of that. This is just a numerical one. We talk about whenever we talk about complex numbers. But now our complex numbers are not going to just be 1 and I. They're going to be 1 and A, B, C. There are three kinds of imaginary pieces. So that kind of makes it mathematically interesting, but it makes it very powerful for dealing with two-level systems, such as optical polarization, which was really the first application of much of this by John Stokes in 1865. So that comes 20 years after Hamilton. Okay, so the spinor components here that we're talking about, I'm going to go ahead and take a sigma dot unit vector. That is AX, AY, and AZ will be components, three components. I'll make them unit vector. I've indicated that with a little hat. Okay, so that will be the A component as opposed to little a component. Just an arbitrary vector component. Here we have very special X, Y, and Z components of some three-dimensional vector. Here I'm talking about a general component of sigma. And this dot product of the sigma, where I'm talking about writing the vector A out into its three components and putting each one of them on the respective X, Y, and Z. So I'm using Pauli's notation for all of this discussion here. So when you go and do that, that is, I'll make that thing, and then you square this just to see what it'll give. I mean, all of these A, B, C operators square up to a plus one unit matrix. What's this going to do? Well, let's make a big mess. I've got 9 components here, okay? And I've got 9 combinations of the numbers X, AX, AY, and AZ, right? So what we have to do is put these matrices next to each other and see what happens. We already know that sigma z with sigma z would just give me a unit matrix, but the more interesting situation here is sigma z times sigma x, for example. So I'm going to multiply these two red and orange fellows together and see what I get. And lo and behold, what I get is this guy. an off-diagonal combination with anti-symmetry. Okay? And if I put an I in front of it, I get the other Pauli matrix. That is very important. That's this one. So Z times X gives me I times Y, sigma Y. And then if I do it in reverse order, I don't get the same thing. They do not commute. But they get something very similar to that. They give minus I times the Pauli Y matrix, the one we call C, okay, the green one. By the way, I'm using traffic light coloring here. The A and the D just make standing waves in various directions. This one is like the traffic light turned green. It makes current flow. That's kind of the way that they makes things go round. So there's a good example of a product of these things. So there's a whole bunch of these. This is XZ, and this minus is ZX, etc. So if we go through and take all of the products that have come here and see how they work out, it works out rather simply. This guy right here cancels that guy down there. This guy right here cancels that guy right there, and these two cancel. I'm just left with a diagonal. So the deal is that when you take sigma A squared, sigma sub A squared, you just get the unit operator times the sum of squares of those components, and this is a unit, assumed to be a unit vector, so you just get 1. So that means that no matter what values you pick for the components of these guys in a combination, you're guaranteed that the square of that, if the combinations come from a unit vector, will be the unit operator. So that's the generalization here. Almost the generalization of complex numbers if I put the i's back on it. If I put the i's back on it, then the square of I times sigma sub A, no matter what the A is, will be a minus 1. Okay. All right, we're getting ahead of ourselves on this other screen here, but that is where we are right now. Now, where does the vector algebra come in? And this is a generalization of what we did. Remember how a dot product gave you one thing and a cross product kind of gave you another? Okay? So what I'm going to do here is go ahead and line these things up again, but this time what I'll do is I'll multiply a sigma A with a sigma dot B. So I've got a bunch of components here, A, X, A, Y, A, Z. I've got BX, BY, and BZ. So we put that together, okay, and then use the multiplication properties that we were talking about before, which are very simple. Okay, X times Y gives Z. It's X before Y. That's actually sigma the way we usually work. Y comes first and then X second if you're reading Hebrew. And as I said, quantum mechanics is a creation by people who mostly read Hebrew, so maybe that's why this comes out. Anyway, here are the three combinations, and it's actually 6 combinations depending on whether you're this way and get a minus or this way and get a positive I times the product. That's the third one out. So what you get here, you see, is the product of any two of these guys is going to be the sigma dot A times sigma dot B is going to give you a unit times A dot B, and then it's going to give you a cross product here with an I times the sigma that you started, the general sigma, whatever that is, and there are 3 pieces to that one, you see. Now this is, have you recall in chapter 10, when we did just a complex number conjugated and then multiplied by another complex number, that's A star B, star means conjugate, not multiply, but it is multiplying. And what you end up with here is a dot product, and then you end up with one component of the cross product. Remember that? So the generalization here is that you get all 3 components in this. all three. It's a three vector. So this is generalizing this complex, really nice, I call it a quick way to review and introduce a vector product. Well, this is a better one because it does the whole job. So that's what I want you to see. That's the spinor vector algebra. Now, what gets a little bit weird, but it's not that weird, and it's weird enough for me to call this the crazy thing theorem. You'll see why I do that, just to make the point that hasn't been made, that this thing is kind of crazy, this whole business here. But what I want to do is I want to generalize Euler's complex. Well, I'm talking about the actual complex numbers, just two components, a real plus an imaginary, to this new thing where I have real plus imaginary x, imaginary y, and imaginary z. I want to generalize that. Okay. So this again was something we talked about in chapter 10, is that the exponential, complex exponential rotates things. Well, it does it here too, except it rotates it in 3 dimensions. That's the important difference, and very, very powerful difference indeed. So what we do here is we go ahead and write out the complex sum here, which, remember, it broke up into a real part with a cosine and an imaginary part with a sine. This is going to do a similar thing, because we're dealing with the same I, whose 0th power is 1, whose first power is minus I, and whose square is minus 1, and whose third power is plus I. And then it starts over again. Okay, so we're trying with this thing the same thing as the just ordinary complex number algebra. So Hamilton is simply going to replace the minus I with minus I, some sigma, the arbitrary sigma. It's got 3 components. So we have some Greek letter here to indicate that this is the phi component of sigma. But it's a component that represents a vector that has 3 components. We discover, since every one of the Pauli matrices squares up to 1, that we can pull the same trick here. We have a repetition after 4 that's exactly identical to the one that's going on for just plain old I. This new kind of I does that. It makes a plus 1, and then it makes a minus I times a particular sigma. And then minus 1 it gets here, and then it makes plus I times that thing, and so forth. You start over. So the deal here is that this generalizes to this. And that's really cool. So when you're dealing with a thing that has 3 components, A, B, and C, or X, Y, and Z, and that's a typo right there. I shouldn't put Z there. That should be C. C rhymes with Z, so it must have screwed me up in that way. But anyway, the 3 asymmetric and the balanced bilateral symmetry, and then the C, the curly guy that moves things, are what we're talking about in physically. So this is the deal. E to that Hamiltonian with a time and a minus I on it is simply the cosine of something associated with the H part here. We've got a sigma of that component, then perhaps multiplied by some number. This one doesn't have to be unit. So that is the basic idea of this. And the way I sum this up, to sort of make fun of mathematics, but okay, to physicists, very often the mathematics can look crazy. This is, if I have some operator, there are things called octonions. They square to minus a big matrix. Okay, so the crazy theorem is that if you have something like I that squares to minus 1, whatever that 1 is, it can be a big matrix or it can just be a number like it is for complex. And the E to the crazy thing times some other, could be a real number, okay, is simply 1 times the cosine of that real number plus crazy thing times the sine of that. Okay, and we see that in two places here. Here, crazy thing is minus I. Plus I would work just as well. You would have a plus sign there instead. Okay? But here, the crazy thing is some combination of the three spinners, A, B, and C, or X, Y, and Z. Okay? And we'll very often put a unit on that thing, and if we do, then we divide by that parameter, that vector length. Okay? So this is a really crazy thing, but it's so powerful, it's so beautiful, as you're going to see. Okay, is this making sense? Is this something that you can take to the bank, at least be confident of getting your return of thought from it? So let's try a few of them. The obvious first one, we can see the answers to that without doing much calculation at all. But if I'm going to use sigma A, that's asymmetric diagonal matrix here, and it has a partner. This is the asymmetric diagonal. This is the symmetric one, the unit operator. We don't have to worry so much about it. It just factors out. It'll attain the quantum overall phase when we're done here. Anyway, here is the expansion that this crazy thing theorem is giving us, and that's pretty obvious. Okay, it's cosine of theta times 1, and then minus I times the sine of theta there. Nothing on the off-diagonal components, and then just the down at the bottom here. I see that I have made a typo here. This should be a plus sign. I don't know how I missed that going through, but anyway, that's an easy one. Both of these are just giving you exponentials out of the diagonal, but there's more.
They're counter phase shifters. Right?
Yeah, that's right. Exactly. Now this guy right here, this is kind of interesting. This guy, which is a cosine times minus I, that's the crazy thing, minus I sigma y, or for us, sigma c, okay? It's got the sine theta in it, according to crazy thing theorem. And presto, this is a counterclockwise, counterclockwise, positive rotation. Okay. And it's done with a minus sign right there. You take the minus sign off, then you get something going left-handed. This is right-handed, counterclockwise. Okay? Now, might as well go for broke here. What if you have all three components? Okay? That's what the crazy theorem would ask you to do. And the answer is you get this as a general driver of a two-state system. There's nothing a two-state system can do that isn't, quantum system, that isn't contained with this operator. This is the total thing. So this is an operator around some vector that has components A, B, and C. Some crank, and that's what we've got right here. What we're talking about right here is the, I'll unloose this thing for the time being. But what I'm talking about here is a representation using the Hamilton operators of a crank that can be in any direction. Okay, have any polar angle and any azimuth angle. Okay, so that is the idea of this particular operator right here, acting on spin up, spin down. We've got to talk about that. That's where this is going to make a connection. But anyway, this is a polar to Cartesian conversion in which you let those coefficients, the coefficients of a unit of phi, A, B, and C, B, this one goes with a cosine, this one goes with a product of a cosine phi and a sine theta. This one is the cosine of the polar angle. That would be this angle right here, and then this phi would be an azimuthal angle in the xy plane of space we live in. Okay, now It helps to test these operators, just to get a feeling for what they do. This one's pretty obvious. It rotates things around the z-axis, and that just amounts to putting a phase factor, so it's really not that different from just a phasor rotation. But this one, as I pointed, is the rotation around the c-axis. That's the y-axis. So that would be this green arrow right here. If you were going to assign a vector to the crank, the direction of the crank, whatever that is, okay? There's my right hand, and there's a thing that will be turning. So all of these things do turnings around different directions, whatever direction you specify, by giving these three parameters, these three Cartesian coordinates. So what you will notice when you do a rotation of an operator is you've got to rotate both the kets. I mean, this thing is made of combinations of ket bras. There's the one that's on the left, and there's another one that's on the right. They both have little flat surfaces that are asking to have a rotation operator attached to them. And in particular, when you turn it to this direction, that's a bra. It operates with a conjugate, in this case, turns out to be the inverse operator to what this was doing. So here is a situation where I am going to do a rotation, just a plain old cosine minus sine, sine cosine rotation of this whole matrix operator. And I can't just do a half-assed job of it. I've got to get this one working on this side, and it will have to be the conjugate, that is Hermitian conjugate of these things. So that means it's just plain the transpose. So put these two together, and you get it looks like a mess at first, but then you recognize cosine squared minus sine squared is a cosine of 2 times the argument, and then that's a sine of 2 times the argument. So what you're getting is a linear combination of the A and the B. That's the A for z-axis and B for x-axis. The actual rotation is around the c-axis, so you don't get any components of the z vector if that's what you were applying it to. So I have here a representation of rotating that thing. So what you're seeing is a doubling of the angle when you specify it in the x, y, and z, or a, b, c space. So that's an important part, is that the 3D rotation, the rotation in the space we live in, is twice whatever happened in the spinor space that's underlying. This is very mysterious sort of talk when you say that everything's made out of spinors. You grow up feeling that everything is vector, but there's hiding behind everything the spinor behavior. They're all made of electrons and protons. They're all spin a half, and that's what we're actually talking about here. So that's one example. Now, if I do it with sigma b, the same thing happens roughly, but this time when I do it to the b, the rotation isn't from here to there, it's from the b down to here. So the same thing happened. This operation, I call it fore and aft, but actually this is the fore and that's the aft. But this is the one I happen to be giving the minus sign to, and it's the one that gives me this combination. Again, a sine and a cosine of twice the angle of rotation, but this time it's involving these two vectors in the way you see it. A minus with a sine and a plus with a cosine of twice the angle. It's always twice. And that's something that we have to get used to. Now, something that I had skipped over very quickly, and I'll go back and catch it right now, is that when we write this thing with a unit on it, we can you know, very easily say, well, that's just the thing without the unit multiplied by the length of it. The length of it is just a good old Pythagorean sum, but with three components, A, B, and C, they may have. And another way to write that is sometimes we're going to be talking, and very soon we're going to be talking about the angular velocity that goes with that Hamiltonian, and we'll use a Greek letter omega to indicate angular velocity. That's actually what the thing, it will be an e to the minus I omega t. So that frequency will be associated with the total energy in the quantum operations. Now, let's get some feeling here. What is a connection between the space that has really four dimensions? The one, the A, B, and C, that makes four altogether, but mainly all of our activities with those three A, B, and C's, the X, Y, and Z's. This is what we're used to. But I'm telling you, behind the scenes are these half integer objects, these things that only have spin up and spin down, and it's spin at half. This is, you know, really strange stuff. It is, you know, you swallow it, you learn it, and you just get used to it. But you shouldn't get used to it. You should say, what in the hell's going on here? What is it up to? What's the universe up to? So here, I'm going ahead, I'm taking the Hamiltonian, I'm expanding it as we just did into A, B, and C components, okay? And I'm using a notation for spinor space. This is a compact notation. H is going to be designated when we're talking about the spinners in the two space, the spin up, spin down, as I'm going to say space. I'm going to use lowercase letters for the omega here, the angular velocity. So I'm using standard notation for what this thing really is getting ready to do, and it's going to be giving us a factor e to the minus I omega t. And here is the asymmetric diagonal, the bilevical balance, and the chiral parts of that, the three components that go into making that vector. And this thing is just kind of along for the ride, but it's the one that determines overall phase going. You can't throw it away. Now, on the other side of the story here is the notation that we use when we're talking about 3D vector space. Okay. Then I like to use uppercase omega. And I like to convert the sigmas into the kind of letter S that I think of when I think of spin. So my angular velocity is a lowercase letter up here for designating stuff in this 2x2 algebra. But when it comes time to dealing with the 3x3, these three components here, and eventually this thing takes care of relativity too. Time is waiting right here, but we won't talk about that for a long time. Anyway, right now it's these three numbers, and what I'm going to do is I'm going to put a half on these guys and put a 2 on these guys so they're equal to this. In other words, I'm going to give you what are the spin operators, not the spinor operators. They're without any half. But the spin operators get a half. They really need that half. And as soon as I put that on there, I got to put a 2 on the parameters that are associated with the 3D world. And we know that in the 3D world, things were going twice as fast, right? We got those 2 times phi rotations when we used the operator, because it took 2 operators to do the job to rotate an operator. So that 2 shows up in the rotations there. So I'm going to take account of that. This is just another way to write the things. And I'm going to use as much as possible uppercase for the omega. That's this thing right here is going to be A minus D is going to be omega. 2 times B is going to be omega B. And 2 times the C here is going to be omega C. As compared to this one, which was 1/2 of A minus D, and just plain B, and just plain C for those 2 coefficients. Okay? So we're making more things, more symbols to work with it, but we have to. These are really different worlds, but they're the same world. And that's just what we'll have to get used to. Okay. All right. So the names I give this, and actually the most common letter used to generalize this is J for Jordan. So the Jordan angular momentum operators, consisting of uppercase S, but you could just as well be uppercase J. They're often labeled that way. Okay, that's fair. Willing to get all the people that invented this stuff get to have their name somewhere in lights. So we'll do that. So let's look at the notation. The notation, the idea was to very quickly be able to write this thing, this e to a matrix, out as a matrix. And we've succeeded in doing that. That's what's going to happen here. E to the I minus IHT is going to come out to be a linear combination of these things. That's the crazy thing theorem, really, right there. So we're going to, these are various notations here. Here's the way the 2D spinor space would be using lowercase omega. Okay, and you can write it as omega dot sigma. Remember, we know what that means. It means this new thing called sigma sub omega, and then it's multiplied by t. There, let's see if I've got that. Looking at that right, yeah. Something a little weird there. Something not quite jive with what I'd like it to be. This little subscript here should be up and a little closer to that sigma because it's multiplying omega to give the t. So basically what we're doing here is we'll do it in this space, 3D space in a minute, but we're writing this thing out. That's crazy thing theorem written out there in the notation that we'll use the most when we come to do spin transformations. But notation for 3D vector space, we're going to go there and use the sort of, shall we say, adult notation, the three-dimensional notation. We'll have an uppercase omega multiplying a spin vector whose eigenvalues are half as big as the eigenvalues that go with the sigmas. And remember, those eigenvalues are 1s and -1, but the S vector has a half, and then the omega goes twice as fast in order to make it. So this thing's going to be going faster by factor of 2 than this thing. But the coefficient here is half as compared to this one, which is just a sigma times 1. Meanwhile, the overall phase is sitting here. We can factor that out at first. Most of the work has gone into working with these three components of a vector. And in the vector space, you do the complex conjugate, which cancels the overall phase, so you don't ever see it. But this is the world that has more information, really, than this one. Okay, I think that kind of does it. Now, the mysterious factors of 2. We really should come back to Earth here, so to speak. I have one more thing I probably ought to say. The crank vector, this guy right here, you'll notice that it's half as big as this one. Okay. Just a minus d instead of a minus d over 2. I got a b here instead of 2b. So when it comes time to do the uppercase omegas, expect something twice as big as when you do the lowercase omegas. So these are the angular velocities associated with, and you got to imagine time going. I'm going to be turning that at some rate, and this thing is going to be doing this oscillation and beating and all the kind of stuff that spin a half and coupled pendulums do. So this is a very deep analogy between two coupled oscillators and spin a half, or any two-level system. Polarization of light is a spinor system. Two components. You're not allowed to use the K vector, right?
But
yeah.
I'm still confused that that 2D spinor is not 2D.
It is in the sense that there are two independent components of the state vector. As there would be if instead of the state of an electron, I decided I want to look at the state of photon. And in case there's two components, two dimensions, describing polarization, x and y, and the complex combinations of those.
But you still have the four terms up there.
Yes, yes. The 2 is the dimension of the actual description. And that is the same here as here.
Mm-hmm.
Okay? But now I'm looking at the thing sideways. I'm treating this as something, the three-dimensional vector is going to be those components. And there you see them. And that's going to be an actual angle if you multiply it by time. If I multiply by time as I have here, I'm getting an actual angle. So I would have a uppercase theta, A, B, and C. That's 3. And we have them up here, they're just multiplied by half. This guy multiplied by half is that guy. I don't know if that helps. But when I say the three-dimensional world, this is what we live in. We live in X, Y, and Z. That we need probably to go ahead a little bit to answer some of that. But right now, the 2 is definitely the size of the matrix. Now later we're going to work with a 3x3 matrix. That's a vector representation of a rotation. This is the sneaky one that's the base of that. This is more fundamental than the three-dimensional vector.
But
Yes.
Pauli's matrices are still 2x2 in 3D.
There are 3 components, actually 4, count time.
Okay.
But 3, let's just do that. I have my hand like that for now. We have 3 components, X, Y, and Z, that are the spinors, X, Y, and Z. And it helps maybe to just look at this guy up here. Here are the 3 of them written out, and these particular S's having a half attached to them. So here's sigma Y right here. So that's the same as the C type or Y spin up. Then there's the X spin up, and there's a Z spin up. So there's 3 of these guys that make up the structure of the three-dimensional world that this is going to be describing. And we're going to be using these operators to do that description. Or we can just look at the complex components and work with complex variables, not real variables. We can work with these guys. And there isn't that much difference, it's a factor of 2. And the reason for that is what I'm going to talk about next. Okay? Yes?
Could I interject
go.
something that'll just take a sec?
Sure.
Well, we've made a constraint that H is Hermitian.
Mm-hmm.
That lowers things
Yeah.
to what we observed.
Mm-hmm.
The Hamiltonian and exponentiation of it.
It constrains its norm.
Yeah.
Well, it constrains it.
Yeah, when you work with the spinors to do that exponentiation, right, you are working with 2x2 matrices. So, and that's a great discovery. I mean, the discovery that just about all our matter, our protons in us, our electrons in us, our neutrons in us, you name them, anything that normally exists in nature, and it's got those 2 components, spin up and spin down, nothing in between. Now you go and get some orbital momentum of 1, now you got 3 components to work with, +1, 0, and -1, and it's integral, it's not half integral. This half integral stuff is the crazy stuff, but it's behind. That is, it has more information than the vectors that you make out of products of the spin half, which we'll be doing later also. Okay, I don't know. It's a strange world. Both worlds. Okay.
It's a good
Okay.
question. Real good question.
We'll answer more questions as we go along. I mean, this starts to give you some feeling for what's really going on. I'm going to be in 2D spinor space, and that just consists of spin up and spin down. That's a pretty common notation. some of the, but Feynman used to use that notation for the two states rather than psi 1 and psi 2. I mean, what's 1 and 2? So I actually use little arrows to indicate them here. This is more things. So this is a 2D world. Okay. Well, I was talking about these complex, in general, vectors that have unitary operators doing them, not nice 3x3 real matrices, but actual complex matrices. This is just a real example. The x rotation has an eye on all the signs. And of course there's the one that has a complex exponential right on the diagonal. That's the z rotation. What we're doing here is a rotation that would be probably my favorite is the A or, I'm sorry, the B or X rotation. So what happens when you rotate a typical state? It starts out spin up, and I'm going to put a magnetic field or something on it to get it rotating. And so it rotates, Here I've written it, I've got it at pi over 6. Beta over 2 is pi over 6, and that's what it's rotating. All of these matrices have beta over 2, rotation angle over 2, okay, on this side of the screen. Over here is the more familiar stuff. I've got an actual spin vector that's pointing in the z direction, that's up, okay, and its components are really simple, and I apply a rotation matrix here. I don't touch the y component, so there's a 1 sitting on the diagonal there, but then the x and the y get to play with each other through cosine and sine. Okay, so I start rotating this thing using the angle beta. Okay, not beta over 2. So everything on this side is slow motion by a factor of 2 compared to what we see in our world as we watch a spin vector turn. Okay, now here's what's really screwy. By the time I get this vector to down, I've only rotated 90 degrees in this space. And, this thing is going to be this thing right here, spin down. You see, is this thing. That's spin down. There's the actual spin vector pointing down, right? So this is up, and there's down. We get down right there. Okay? This thing's so slow, it's only half done. This thing is rotated all the way around to down. Okay? That's our full rotation to 0, 0, minus 1 from what we started with, 0, 0, 1. Okay? We went through these states right here in which the x component got some show time, but that's all going to be gone when we get to here. Pretty neat, huh? Except that doesn't answer the question, what happens next? I keep going here, and I end up back to spin up, but it's a minus spin up over here. And that's on the next page. I'm going to go over here and get this thing caught up so I can show what happens next. Okay? The idea is that this guy right here is a state that has a phase of pi, e to the I pi, which is minus 1. There, on the other side, we're back home. Okay. We would say that that's a complete rotation, and I'll do it very quickly on this screen. There, I'm finished. I started down, I kept going over to here, and finally up. Okay, so there's a spin is back to up again. I feel like I'm done. But that's because I'm just one of those three-dimensional people. I'm not working in that four-dimensional complex space, which I have to start thinking about if you're going to be in this business. So that's the cool thing. This is only halfway home after 2 pi. 360 degrees of rotation over there. In other words, and this sounds like Donald Trump talking, spin down is up. right? Up is down, right? I mean, that's how crazy this is. So this half-fast business here is showing its effect very much, and that is an interesting thing. Now, we have a little bit of time here. I think we can take a little look at the Hamiltonians that come up as we do this. Here's a typical Hamiltonian that involves spinors. This is the most elementary of quantum mechanics. This is where I apply a magnetic field to some object, say an electron, could be a proton. It's not too easy to do this with a neutron because its magnetic moment is really tiny, but it has a spin and a half. It just happens to have really very tiny magnetic moment. But electron, that's got a really big one because it's pretty light. The gyromagnetic ratio depends on something it involves the spin of it in the denominator, gyromagnetic ratio. So sigma dot b is what we're talking about, and here's the sigma vector, that's just the Pauli spinors, and then here's the z component of the magnetic field, the x component of the magnetic field, y component of the magnetic field. And here I'm abandoning for a brief moment here the A, B, C that I was using before. I bring it back right there. Okay. So this is the notation for this Hamiltonian in 2D spinor space. And we can take that and say that the theta, that's big omega t, is defined by this Hamiltonian, okay? And it's the thing that's driving the spin of the object. If I apply the little suction cups to this thing and hope they don't slip, and one of the ways to do that is make it pretty tight, so I tighten it down there. And then basically what I'm going to do is rotate the spin vector, which is pointing out what is the z-axis right there. The z-axis of the body frame of this ball, okay, is there. So right now I'm rotating the thing, and there are three angles, the Euler angles, that's what we're going to be talking about. The three Euler angles that describe rotation of a rigid body. We're taking on that problem right now just in order to make this mechanical analog for the precession of the spin that results from applying a magnetic field to something that has a magnetic moment, a spin with some gyromagnetic ratio that's non-zero. So this vector omega here is that crank vector. The vector s is the instantaneous location of the spin, and that's all there is to basic, fundamental, single-frequency resonance of a two-state system. Now what we're going to do is we're going to show that each one of these possible directions, A, B, and C, correspond to different kinds of two-dimensional oscillation of coupled things. That is what we will be doing next. But before we do that, I want to take the last few minutes here of our time to make sure that we see. Now, these are links to something that more or less works. This is what I'm talking about, links to the Euler machine. Is actually online, but it's not one of those things that is working very well yet. But in any case, the three dials here indicate what you need to know about the spin. It includes its intrinsic phase as well as the other two components, is just where it points. It has a certain polar angle and it has a certain azimuth. Well, we need to do all three carefully not just those first two. The alpha for azimuth, the beta for polar angle. Beta rhymes with theta, polar coordinates. Alpha for azimuth, usually phi in calculus books, and beta is usually theta, and they don't bother with the third one, which is that dial that's pointing at you, or more or less at you, at the very bottom of the sphere. Okay, that's the one that's keeping track of quantum phase. So this is a mechanical object that's as far into that two-state system as I can get. It is showing you the numbers correctly. It's just that very often you have to take those numbers and multiply them by 2 to get the answers you're getting. So to understand Euler angles, I built this thing, but I also had in mind that it was going to be a model for rotations of spins and any two-level system behavior, which was getting very popular at the time I put this thing together. And it all happened by accident. I did a picture, a very crude drawing of something like that, and it got accepted in the reviews of modern physics, which is a big deal to get a paper in there. And it was the first or second figure in that review article. And I was at JILA, Joint Institute of Laboratory Astrophysics, what it used to stand for. They don't do that anymore because the joint meant with National Institute of Standards and Technology, and government said, well, we've got to divorce those two. Anyway, there was a machinist, and not just a plain old machinist, a real instrument maker at JILA that was doing all this stuff for lasers, and he saw that figure and he says, I want to make that. And he just went around and got junk in his shop and made a very big one of these things. But he had rings all the way around. You see, there's a ring here, and then there's another, just like a gimbal of a gyro, which he actually knew about. And that was the point, as soon as we started playing with it, we realized it kept running into the gimbal mounts. So when I got to, shortly thereafter, left for Georgia Tech, and at Georgia Tech, we literally built this thing. And you see it has only quarter cycles, so it doesn't run into itself as often. But anyway, the basic idea of this thing is to characterize a rotation by Euler angles in a way that makes sense. And the idea is that you start off with this thing right here with these two dials lined up. And that's was no-no for a gyroscope. It's called gimbal lock. But anyway, at that point you can turn the gamma dial, which is this one. It's the last time you'll be able to do that. The next time you still have the thing lined up with the beta on the y-axis, so you apply a y rotation to that. And then you follow that with another z rotation, just like this one, but now you set the azimuth. So the azimuth is set last, this comes first, and this is in between. So that's what you do to get the rotation matrix for arbitrary alpha, beta, and gamma. Here's a z rotation, and it's a rotation with your right hand, so the minus is on that side of it. Then this is a rotation by beta, okay? It's also a rotation this way, but now the minus is down here, as you probably realized when you did that problem where we worked out polar angles. And then this is just another one, but by alpha, that's just like this one, but they don't commute. So together they build a matrix like that. So here are the new unit vectors that result from doing that rotation of something that was originally pointing in the z direction. Okay? And there's your polar coordinates right there, representing the spin vector in 3 dimensions where it points. And then the other 2 axes, x and y, are up on the equator of that thing, and they have fairly complicated components. But that gives you the thing in the thing. And then here is this is the polar coordinates in the frame. If I was the spinner being that lived with this thing. These are the coordinates that I would use. These are the coordinates associated with x bar, y bar, and z bar, which are the coordinates relative to this coordinate system. So you just read those off right here. The only difference is that the angles have turned minus, the way the people in that reference frame see our rotations as clockwise, left-handed. And so you just put a minus sign on all of those angles there. It doesn't change that number. It doesn't change that one because the minus times a minus is plus, but it does change this one because that one affects it. So other than that, there's three coordinates that are associated with the actual, whatever it is that lives in a spin. Okay, so I wanted you to see that before we go on. This is, I think, important sort of relativity. This is the relativity of one coordinate frame relative to the one we're used to. And that one is a coordinate frame that has that spin vector. And that's it right there. Okay, I think we'll just stop at this point. I'm going a lot slower than I used to on this subject, but I think you have to because it's so weird. It's something that you need to make sense of if you're going to be working in quantum anything. Okay.
You might mention that the board app,
To which?
the box, Jesus, or web app that we've got a link to there.
Oh, this guy.
No, not necessarily that, but the one that actually shows the Stokes plot in
Okay.
3D as well as the two-state plot. You can play that at home and rectify the 2D, 3D in your mind a lot better. Just they'll run at the same time.
Let's get that link.
Oh,
If
it's there later in the.
I don't know if.
Go down to one of those A/B pure settings there and we'll let her rip. And it is on our front page, a reference listing.
Okay, now there is a problem with that because of all of the
It didn't get in.
rain and snow.
It was in from last. Go ahead and go into the one you
Let's-
got because it'll show the
Let's
rest of
go.
the last lecture.
Yeah, let's go to the beginning.
We'll make this quick. This
Yeah.
is worth this because you can
Yeah.
work it at home.
I'm just going to the beginning of this one, and then you say it was already in.
The front page, there it is.
You got it?
Um,
And show me.
right down there, box at web apps.
Okay.
Go ahead and just pick the A type or
All
the
right,
B
let me-
type. I'm pointing on this column, second group from the bottom.
Okay.
I wish I had a pointer.
Yeah, you
This is
need a
always a
laser.
pain in the butt,
Yeah.
trying to
Oh, you're
pass
talking about this
information
guy.
the other way. Choose
Okay,
one of
that
those.
guy right there. Okay. For example, A type.
Yeah,
Yeah.
start with what we just, or the B we do too.
Yeah. Is that, yeah, that's. Now, this
That's
is
A
the-
type.
This is the one that has spin up. I just put the spin right on the A axis, asymmetric diagonal axis. If I hadn't quite put it on that, like if I just missed it by a little bit, I would have gotten, you would have seen the spin vector there, and you would have seen motion inside that.
See, we're not moving our S spin vector at all with this Hamiltonian. If we choose other combinations of A, B,
Yeah.
C, and D,
You can see the,
we will.
yeah, this one has an S on the B axis, and that makes it bilaterally symmetric. So this is not the A type, this is the B type. And it has spin up, and then spin down is here. And spin almost down is there. So you see the spin vector a little off of what is down B.
Give it a smidgen B just so that we can see that spin vector move due to the Hamiltonian.
Oh, turn on a little B.
Yeah, let's do NMR.
Okay. Let's see if I can see that. Turn on the B here.
Just slide her a little.
Yeah. Just give it a,
That's
that's a
enough.
lot, that's too much, right? I'll lower that down a little bit. See if I can get that down to 0.7 or so. 0.6 would be good. Okay, let's just go ahead and reset T0 on that. So what this is going to do is give you a Lissajous pattern of some kind. Depends on what the other numbers are. But this corresponds to a spin resonance. It's making the spin go around. And guess the way we've got it right now, that, let's see, it's hard to see where that guy is, but it's definitely a rotation around the B axis, bilaterally symmetric axis. So
Negative.
these are all things that,
Left-handed,
yeah,
because it's on the other side of the B
Yeah.
label. That's
Yeah,
it's hard to tell the labels are positive.
the rotation of the spin vector is left-handed in this particular case. That's what you get when B is positive. If B is negative, then be the other way. In any case, that's
Which is more NMR-like, right?
that's a connection with the C. The C probably is a better one to look at. Let's go ahead and come back to that, and I'll just pick out the C type thing. Do we have one of
Well,
those?
see, since that was for the last lecture, we didn't
Yeah.
include C because it wasn't in the lecture, but you
Yeah.
can tweak it.
Let's go. Let's see if I can.
Take the extant B that you got running,
Yeah.
change it.
Let me just go ahead and do that particular one right there. There's a very long resonance where the S vector is just rotating around the bilaterally symmetric thing, but with equal components of everything. And that's definitely a perfect B type thing. We'll go through this step by step
Yeah.
in the next lecture.
Let's just see
There
if
it
we
goes,
can
and now it
create
starts over again. Retracing the steps, just a little bit off. It's 0.05 compared to 1 and 1, so it takes a long time before you fill up that square. What I'll do here is I will pause and go to controls, and I will turn off the B. See if I can
You
do-
could double click in the text cell and turn it to 0 with your keyboard.
Okay, double.
Or you can delete the characters at the
I can
tail
just
end.
go like
You
that.
know, it's a little finicky.
Yeah.
I mean, especially when you're standing above the keyboard.
And I'll turn this one on, a little bit of positive,
Perfect.
and go ahead and let that go. So this is when you put the crank along the C axis,
Yeah, there it
and what you get, depending on what you started with, is rotation. In other words, there's an ellipse that's being rotated. That's circular dichroism.
is. Like a sped up focal.
Yeah. If I
Extreme
erase
focal.
paths and start right on this axis right here, you can see it simply makes a pirouette. And the smaller I make that C, the longer it takes to do a rotation. But if I go here and make a circle to start with as my trajectory, and I can do that by going out about that far. I'm going to erase all the paths. See if I got more than I bargained for there.
Yeah. Once you pause it, erase paths.
Erase paths and pause. Erase paths. We gotta fix it so when you erase paths, it actually does erase. I'm going to try to do that again by going here. And I do have, according to this thing, C equals something. A and D equal, so that shouldn't, think,
There you go.
there we go.
Virtually circle.
Pretty close to a circle. I'm surprised I didn't get one because I thought
You can hand key the momentum in so you can make those units, and that's what I do when I set up the lengths.
Anyway, there is something very close to circular polarization, but it hasn't, because I didn't get it perfectly oriented. You see the spin vector right down there? It's pirouetting around.
Negative.
What I can do, I guess, is move this thing out there and then adjust it so that the spin vector
Yeah.
is sitting right
Sure.
on the axis, and then let it go and erase paths.
Yoda.
And I've got a perfectly circular polarized thing. With left-handed, it's minus C, so that's left-handed polarization going on there. But every one of these classical analogs has an exact spin a half correspondence. So we're kind of making our world in the three space, A, B, and C space, is where you can visualize what you're going to get. You know, every point in there corresponds to a certain situation, certain Hamiltonian. And then that Hamiltonian is exactly the same as the one which you use to resonate a spin, or get a spin cycling. To resonate it, you actually have to change the Hamiltonian. That's parametric amplification, parametric effects, but we'll get to those too. But for the time being, I want you to understand the ABCs of quantum mechanics.
Yeah. Out online, we have that second page with all the references that is used in this lecture, so you will find C and B in there if you want, the mixed types if you want to play. But, and then they're just click, and it'll take you there, and you won't have to worry about hand keying anything until you play even further and deeper.
Okay.